We illustrate here a recent result about the generalized Poincare-Hopf result in graph theory. It deals with a problem to count complete subgraphs of a finite simple graph. This is called the Clique Problem. It is one of the classical 21 problems of Poincare, which are NP-complete. This means that if we could solve the Clique problem fast, we could solve any NP problem fast. Poincare-Hopf is a result in differential geometry. It is usually formulated for vector fields on a manifold. The Euler characteristic of the manifold is the sum of the indices of the field. It's a theorem. It's important in Morse theory, where the vector field is the gradient field of a scalar function g. In the Morse case, the indices are then either 1 or -1 at critical points of g. In the discrete, we deal with a general finite simple graph. The Euler characteristic of the graph is the super sum of the Clique cardinalities. In terms of the f function, which you see here, the Euler characteristic is 1 minus f of -1. It is -10 in the example which is given. The discrete Poincare-Hopf theorem deals with scalar functions on the vertex set of a graph. It is assumed to be locally injective. The index is 1 minus the Euler characteristic of the part of the unit sphere where g is smaller than the value of g at x. The result holds for any graph. Here's an example with a random graph. The f vector is 14, 36, 16, and the Euler characteristic is -6. The indices are given at each point. They add up to the Euler characteristic. I obtained this result in 2012. Here's another example, which is more geometric, as it's a discrete manifold case. It's a two-dimensional sphere of the form of an icosahedron. We have chosen a function g where the indices are either 0, 1, or -1. New is that we can formulate this in function form. The f function of a graph is the sum of the f functions of stable spheres for Sg multiplied by t. So that's the new result. Here's an example with a house graph. We see the function values of g in red, and the index polynomials are given at the center of the nodes. They add up to the f function of g. In the special case t equal -1, we obtain the older result for scalar indices and Euler characteristic. But now we can use this to recursively compute the f function. And what is nice is that in every step we have then n smaller graphs, usually half of the unit spheres of the nodes, which in general are much smaller and in general can be computed in sub-exponential time. So here is a kind of cliche example. The torus, the function g is given by a linear function on the ambient space, leading to a Morse setup with 4 critical points, the maximum 2 saddle points and a minimum. So this is the classical case. Now in the function case, discrete manifold, the torus as a discrete manifold, and we have given the polynomials at each point, and they add up, we multiply by t to the f function of g. Thanks. For more information, you can look at the paper which is on the archive.